What the heck?
Tagon.
Hello, hello, hello! Welcome to the next
Wacky Calc Wednesday!
Today we're going to be doing a sorta just for fun integral problem. Sort of akin to the original Wacky integral videos I did months and months and months ago, using like powers of tangent or powers of the natural logarithm of x. Because today we're going to do an integral over powers of the Lambert-W function. That's right, we're keeping this W train going. So let's get into it. It's a pretty neat answer. It involves the gamma function in some regard, but not entirely. So before we explain what the integral is, let's just do a quick review of the graph of the Lambert-W function in the xy plane, so just a real input for now. So we know that if y equals x times e to the x, that therefore x equals w of y, where this is the Lambert-W function. And we can sort of figure out what this graph has to look like by simply observing what the graph times x times e to the x looks like. So if we give ourselves an xy plane here, we know that this function has to be 0 when x equals 0, because it's going to be 0 times e to the 0, which is 0 times 1, so 0 there. At 1, it's going to be equal to e. Right, so at 1, it's going to be about there. And as you can see, this is just going to shoot up very quickly, because we're multiplying larger and larger positive numbers by even way larger and larger positive numbers. And we can see that as x goes to negative infinity, if you just simply do L'Hopital's rule, you can see that this number goes to 0 way quicker than x goes to negative infinity as x goes to negative infinity. So this will actually start to go negative, but then it will sort of taper off and back up towards the negative x-axis as an asymptote. And so it looks sort of like that. And if you do take the derivative of this, you get, what do you get? You get y prime equals e to the x times 1 plus x, right? Now, this means that the derivative is equal to 0 at x equals negative 1, right? So this point right here has to be negative 1, right? Where the curve is flat, right? Because e to the x is never 0, so the only way for this to be 0 is for 1 plus x to be 0, which is when x equals negative 1. And all you have to do is plug negative 1 into here and see that the height of this function here has to be negative 1 over e, right? Because you get negative 1 times e to the negative 1. So this point right here is negative 1 comma negative 1 over e. And that's going to be important because when we invert this function, we should also point out that if we plug in 0 into this, we get 1, which means the derivative of this function is 1 at 0. So the slope right there at 0 is 1. Okay? And clearly it tapers off here and shoots up very quickly there. So when we invert this, it's going to just reflect like that. And because it's got a slope of 1 here, it actually just nicely goes like that. And doesn't, it's not secant to itself, it's tangent to itself, essentially. And so it just does that. And now what I'm going to do is I'm just going to simply erase all the other stuff, because this function here is x times e to the x, we're inverting it, so we get the w function here. If you study complex analysis, you'll understand that the w function has branches, and so it is a, quote, multi-valued function. That may seem odd if you only know about functions given the definition that they have one output for every input. I understand that that can be a little confusing, but essentially there's a way in which you can describe more than one output for a given input depending on the angle that the point takes in the complex plane, but the point is we're not doing the complex plane right now. And so what we're going to do, this is the integral that we're going to solve. So we understand that on the right side of the on the positive x-axis, this area under the w function is quite large and infinite. But you'll notice that if we take a look at, oh, by the way, because this corresponding point on x times e to the x, that was negative 1 comma negative 1 over e, that means that this point is negative 1 over e comma negative 1. That's probably much easier to see right there. So we're going to consider the area from there to 0. So we're literally just going to consider this tiny little underhang, because at that point it bends back under itself. So this is sort of the negative first branch of the Lambert-W function. It's like sort of the other value that you can possibly take. So this is W0 and this is W negative 1. There's infinitely many branches with integer values for the index of the branch. And so we're just going to find the area under there, but more specifically powers of that area. Now I want to be careful. I don't want to do this integral, the integral from negative 1 over e, or negative e to the negative 1, to 0, to 0 of w of x to the power of, or I'll use t and then x is the power. I don't want to do this, because then I'll be taking continuous powers of a negative quantity. So I want to start off by right away multiplying w of t by negative 1, so that I start with this area up here, and then I'm taking continuous powers of a positive amount, so I don't end up with complex values and I don't have to worry about certain things. So it makes it easier, and I think it's easier to understand. You sort of have to do the same thing with the natural logarithm function when you do the integral over powers of that to derive the gamma function. And I did a video on that as well, and I'll link to it right now. So we want to solve this integral right here, but not necessarily solve it, because there's likely not a nice closed form expression in terms of elementary functions, but we want to sort of get a good idea of what it equals and what it might be related to. So I hope this was refreshing enough. At some point when I start exploring contour integrals over the Lambert-W function to arrive at very, very cool results, I'll have more of an explanation of like the properties of this function and also the complex analysis involved. Because I do plan on doing a series on that, remember. At some point, once I've gotten all of my one-off things done, I will be using this textbook to do my own presentation on complex analysis. So let's take a look at this integral now, because now that we understand what's going on, we can attack this problem. So the integral that we want to consider is from negative 1 over e to 0 of negative w of t to the power of x minus 1 dt. Now, before I said to the x power, what I meant to say was to the x minus 1 power for convenience later down the line, and that may clue you in on what type of function we should expect to see popping up just by virtue of knowing about special functions. But we're just going to go with the flow for right now. So the substitution we're going to make is quite simply u equals negative w of t. Now, if we multiply the negative 1 over, we get negative u equals w of t. We can then use the inverse of w, which is t times e to the t, on both sides, and we get that negative u times e to the negative u is equal to t. Which tells us what? That tells us that dt is equal to, well, if we do the product rule, we have to take the derivative of the first term and multiply it by the second. So we get negative 1 times e to the negative u. And then we have to keep the first one and take the derivative of the second. So we get negative u times negative e to the negative u. So plus u times e to the negative u, and that's all times du, which is, of course, equal to, factor out the negative e to the negative u, and we get negative e to the negative u times the quantity 1 minus u du. And that's what dt is equal to. So we can do our replacements now. I'll do the bounds last. So we're replacing negative w of t with u, and that's to the x minus 1 power. And now all we have to do is replace dt with what we know it to be equal to. So we're going to have negative e to the negative u times 1 minus u du. It's as simple as that. So now let's take a look at the bounds. Well, we know that these are the t values, and so we can simply plug these t values into here. If we want to get negative 1 over e, well, that's the same thing as negative 1 times e to the negative 1. Which means if we want this to look like negative 1 times e to the negative 1, that means u has to be 1. So the lower bound of this integral is 1. And if we want t to be 0, we would just need to plug in 0 for u, because e to the negative 0 is 1 times 0 is 0. And so the upper bound is 0. Now that's a little confusing, right? The upper bound is less than the lower bound, but of course we have a couple of ways to distribute a negative to make it not the case. So we'll just use this negative right here that's being multiplied onto e to the negative u to reverse the bounds, right? So we simply switch the direction of integration, and that's the same as multiplying by -1. And now all we have to do is distribute these terms into this little difference here and break that up into two integrals. And we have these two integrals now. So we have the integral from 0 to 1 of u to the x minus 1 times e to the negative u times 1. So times e to the negative u du. And then we have to multiply all that by negative u, so we get minus the integral from 0 to 1 of u to the, I won't say x, I'll say x plus 1 minus 1. That's the same thing as x, right? X plus 1 minus 1 times e to the negative u du. Now, these look rather familiar, or they should look rather familiar, because if you consider the gamma function, this is equal to the integral from 0 to infinity of u to the x minus 1 times e to the negative u du, if you're at all familiar with special functions. And you can use integration by parts to find a recurrence relation that shows that this is quite literally equal to x minus 1 factorial for non-negative integers x. These are sort of similar, but they're not quite there, right? They don't go all the way to infinity, they only go to 1. In fact, they're called the incomplete gamma functions, or more accurately, the lower incomplete gamma functions, because there are two incomplete gamma functions. So what we'll talk about now is just introduce those. So these are the incomplete gamma functions. There is an upper one, usually denoted like so. So capital gamma of s comma t is the integral from t to infinity of u to the s minus 1 times e to the negative u du, right? So you're starting somewhere that's not 0, and you're going up to infinity. And the lower gamma function is a lowercase gamma, sorry, not oily macaroni, s comma t has two inputs, is the integral from 0 to t of u to the s minus 1 times e to the negative u du. So as you can see, the lower one goes from 0 to a point, and then the upper one goes from that same point to infinity. So you can actually quite quickly deduce, so this is the lower one, sorry, you can quite quickly deduce that big gamma of s comma t plus little gamma of s comma t has to be equal to the regular gamma function of s, because it simply completes the whole interval, right, from 0 to t, and then t to infinity. It's the entire interval. And again, another fact is that upper gamma of s comma 0 is also just the gamma function, right? Because if we plug in 0 for t, then this is the integral from 0 to infinity of all that stuff, which is just the gamma function. You could also say that it's lower gamma of s comma infinity, quote unquote, right? Let t go to infinity, then that is also a valid way of representing that. But notice that we don't have the ones from something to infinity, we have the ones from 0 to something. So both of these are examples of the lower lower incomplete gamma function. So we're going to quickly take a look at one of its properties, because we're going to need it to sort of relate these two integrals together, because they're the same function, just off by 1. And so we need to find the recurrence relation for the lower incomplete gamma function. And so given the definition of what we just discussed, this has to be equal to little gamma of x comma 1 minus little gamma of x plus 1 comma 1. But I want to sort of put both of these in terms of x instead of x plus 1, so I can combine them in some way, because it's quite interesting how they relate. But first we need to sort of find its recurrence relation, so I can put the x plus 1 in terms of x. So let's take a look at the general little lower incomplete gamma function. So little gamma of s comma t is equal to the integral from 0 to t of u to the s minus 1 times e to the negative u du. And so we're going to have to do integration by parts, so we'll pick u to the s minus 1 to differentiate, and e to the negative u du to integrate. So we take the derivative, we get s minus 1 times u to the s minus 2 du, and we integrate e to the negative u, and we get negative e to the negative u. So we need to multiply those and subtract the integral of those two, which is quite easy. So we get negative e to the negative u times u to the s minus 1 from 0 to t, minus this integral, but that minus is going to cancel with that minus there, so we get plus s minus 1 times the integral from 0 to t of u to the s minus 2 times e to the negative u du, right? And now we can plug in values into here. If we plug in 0 for the lower bound, this 0 here, 0 to the s minus 1 is going to cancel it, so it doesn't matter. And if we plug in t, we get negative t to the s minus 1 times e to the negative t. So that's sort of, once you've picked s and t, this is just some constant, right? You just plug the numbers in and you just get a number. And here we have plus s minus 1 times the integral from 0 to t of u to the power of s minus 1 minus 1, right? Because s minus 1 minus 1 is s minus 2 times e to the negative u du, and this of course simplifies to be s minus 1 times little gamma of s minus 1 comma t minus t to the s minus 1 times e to the negative t. So this is the recurrence relation for little gamma, or the lower incomplete gamma function. And so because we can write little gamma of s comma t in terms of little gamma of s minus 1 comma t, we can write little gamma of x plus 1 comma 1 in terms of little gamma of x comma 1, simply by using this relationship right here. So let's do that now. So all we're going to do is rewrite this. So we're going to keep the first one the same. So we have little gamma of x comma 1. But now let's just plug these two things. This will be our s, and this will be our t. Right? And so we're just plugging these things into here. So x plus 1 being plugged into s minus 1 is going to be x plus 1 minus 1, so just x, right? So we first get x times little gamma of x plus 1 minus 1, so x, right? That's what we wanted. We wanted to write it in terms of x. T is just 1. And then we have minus 1 to the power of s minus 1. Well, we're doing this on the real number line, so for our purposes here, 1 to the power of any real number is just going to be 1, so we don't have to worry about that. And then we plug in 1 here, so we get minus e to the negative 1. So we essentially get this funky little constant out the front, but that's just the way it is. And so we've used the recurrence relation there. And then we can sort of simplify this a little bit more by grouping things together and moving them around. And if we call, by the way, the original integral, we'll call it I of x, just for simplicity, right? That tells us that I of x, this weird integral over powers of the Lambert-W function, is equal to... Oh, I made an error, by the way. This is a difference, so this should be subtraction, and this should be addition. My mistake, right? Because we're subtracting this, and that negative had to be distributed onto those two terms. So that was an error. My bad. And so we can simplify this by writing it as 1 minus x times gamma of x, comma 1 plus 1 over e, right? E to the negative 1 is the same as 1 over e. So let's see if we can evaluate some of the values, right? Let's take a look. So it's quite clear that I of 1, right, if we were just to consider it from the get-go, I of 1 is the integral of from negative 1 over e to 0 of negative w to the power of 1 minus 1, which is to the power of 1 minus 1, which is 0, so it doesn't really matter, and still with respect to t. So this is just the integral over 1 from negative 1 over e to 0 dt. So that simply gives us 0 minus negative 1 over e, so we get positive 1 over e. So that's not too hard. I of 1 is positive 1 over e. I of 2 is a little more interesting. We actually get the Lambert-W function to the power of 1, but with a negative out the front. And so we get negative, the integral from negative 1 over e to 0 of w of t dt. For this you need to know the antiderivative of w of t, and as it turns out it is t times w of t minus t plus e to the w of t. I promise. And this is from negative 1 over e to 0. And we have that negative out the front. So let's see what number we end up with. So we have to plug these numbers in. If I plug 0 into that, that's 0. If I plug 0 into that, that's 0. If I plug 0 into that, I get 1, because it becomes e to the 0. So I get minus 1, and then we plug negative 1 over e into all of these things. So w of negative 1 over e is negative 1, times negative 1 over e gives positive 1 over e, but we're still subtracting it all, so we get minus 1 over e anyway. And then we're subtracting a negative thing here, so we're going to get plus t, but we're plugging in negative 1 over e, so we're going to get minus 1 over e again. And then we're plugging in negative 1 over e into here and subtracting this because this is the second part of the definite integral. And so we plug in negative 1 over e into there and we get negative 1 again. So we're again subtracting 1 over e. That's fun. And so what we end up with is, can we even see this anymore? Yes, negative e over e, because that's 1, right? Minus 3 over e. So in the end, we get 3 minus e over e, which, if I'm not mistaken, is about 0.103. So that's what you get if you do I of 2. I of 3 is a little harder, and you sort of have to work it out on your own. It's a little iffy, but they're fun nonetheless. It's very cool integrals. These are the only two you can really solve right off the bat. You sort of have to figure out powers of the Lambert-W function as well, or maybe use this function. I don't know how easy that is to use, but this is the answer, right? This is sort of the final answer. This is what I of x is equal to. That's what I wanted to set out to prove today, and I did. And so there's clearly a neat connection between the Lambert-W function somehow and the gamma function in some way, sort of in an incomplete way by using the incomplete gamma function. And so I hope that was sort of interesting, an interesting little foray into some special function stuff, sort of combining them together in one little go. So thank you very much for watching, and my challenge is coming soon, Papa. I will destroy you. Bye-bye now.